This is an introduction to the idea of moments and center of mass. We'll see later in class how to use integrals to find an object's center of mass, which is the point about which an object balances. Imagine taking an object, perhaps a baseball bat. Then imagine trying to balance that bat on a single finger, and we could think maybe the point of balance would be somewhere about here, where the bat would perfectly balance at just one point. That is called the center of mass of that object. To simplify this, let's consider just two masses rather than a whole continuous object. And we're going to think of something called the law of the lever. If we have two masses, m1 and m2, that are both placed a distance d1 and d2 respectively about the point of balance, then the first mass times its distance is the same as the second mass times its distance. This means that if the second mass is larger, then the distance will be shorter to the center of mass. And if the first mass is smaller, then we'll have a longer distance. This is called the law of the lever. Using this principle, we can develop a formula to find the center of mass for a system with two objects. If we have a mass m1, which is placed at a point x1, and then m2 placed at x2, we want to find the center of mass x bar of the system. So we'll just draw in an x bar, maybe it's somewhere about right here. And we want to use this principle, the law of the lever, in order to find values for this center of mass x bar. First, we want to think of the distances between the objects and the center of mass. The distance between x1 and x bar will be the difference between them, x bar minus x1. So this distance is x bar minus x1. And the distance to the second mass will be the x-coordinate of the second mass minus the center of mass. So we have x2 minus x bar. These would correspond to the distances d1 and d2. So we can write this sort of a formula applied to this scenario. We have m1 times the distance to the center of mass, which is x bar minus x1, and that equals m2 times its distance to the center of mass, x2 minus x bar. Now that we've got this formula, we are going to solve for x bar. Start by distributing the masses on both sides, m1 times x bar minus m1 times x1, distribute on the other side of the equation. And now I'm trying to solve for x bar, so I want to isolate those terms together. I'm going to move the m2 x bar over to this side of the equation by adding to both sides, and then I'm going to move this m1 x1 to the other side. If I do that, I have m1 x bar plus m2 x bar equals m1 times x1 plus m2 times x2. Now I'm going to factor out the x bar from both these terms. And this still equals m1 times x1 plus m2 times x2. And now I can solve for x bar simply by dividing both sides by m1 plus m2. So the formula for the center of mass is x bar equals m1 x1 plus m2 x2 divided by m1 plus m2. Notice that the denominator here is just the total mass of the system. These expressions in the numerator are called moments. This formula gives us the perfect balancing point between these two masses. Let's generalize this now to a system where there are more than 2 points. Suppose we have a lot of different objects with masses m1, m2, up to m sub n. So we have n different objects, and these are all distributed at the points x1, x2, up to xn along the x-axis. The total mass of this system is denoted by small m, and that's just the sum of all these masses. So small m is just m1 plus m2. We just add all of the masses together. The moment of the system about the origin is just the masses times the distances all added together. So this would be m1 times x1 plus m2 times x2. And we keep doing this until we get to the last one, m sub n times x sub n. That is called the moment of the system about the origin, and we denote that with capital M. Then the center of mass is just the moment divided by the total masses, capital M divided by small m. This is a generalization of the formula that we just saw for two masses, and this can be applied to any number of masses distributed along the x-axis. Let's work through an example where we apply this formula. In this example, 5 objects are distributed along the x-axis, and we're given these coordinates. These are the x values, and here are the masses. These are the m values. And let's try to draw a little picture here so we sort of visualize what's going on. We have the x-axis. Let's say this is the origin right here, and then -6, -1, 0, 2, 3, those are x values. So -6, that's right about here, -1, right about here, 0, and then we have a point at 2, and then also an object at x equals 3. And then let's draw in some masses, and we'll try to draw them having a size kind of corresponding to these values here. So at -6, we have a mass of 7. That's pretty large. So here's the first mass. At -1, we have a mass of 2. That's kind of smaller. And then at 0, we have a mass of 3, just a bit bigger. At 2, we have a mass of 1, very small. And then when x equals 3, we have a mass of 5, a little bit bigger. We want to know at what point do these masses balance? Where is the center of mass for this entire system? So we'll start by finding the total mass, then we'll find the moment of the system about the origin, and then we'll use the formula that we just developed to find the center of mass. The total mass is just the masses added together. We call this small m, and this is literally 7 plus 2 plus 3 plus 1 plus 5, which equals 18. The moment of the system, capital M, this can be found by multiplying each coordinate by the mass at that point. So we take -6 times 7, and then we add -1 times 2, plus 0 times 3, plus 2 times 1, plus 3 times 5. This is called the moment of the system about the origin, and we just add the masses times the coordinates. We compute all those, multiply those together, and then add up the results. Working through the arithmetic here, we get a value of -27. That's capital M. So the center of mass is x bar, which is capital M over small m, the moment divided by the sum of the mass. This is -27 divided by 18, which simplifies to -1.5. So at -1.5, right about here, that is where the center of mass is of the system. We could balance all of these masses right about that point. They would perfectly balance around that point. So far, we have not seen where calculus fits into this, but we've laid the foundation for the ideas of center of mass and moments so that in class, you'll see how to use integrals for more advanced examples.